let's take a look at Green's theorem in circulation form. Now, from the fundamental theorem of calculus, we wrote it before as the integral over the interval of AB df dx is equal to FB minus FA. Okay, this is the fundamental theorem of calculus. And we talked about how you're trading a derivative in the bulk, the whole interval AB, for an operation at the boundary. Okay, and we also looked at that with the fundamental theorem of vector line integrals and also the operations on stream functions. Well, one way to also look at the fundamental theorem of calculus, a sort of motivation of why it works, is if you could take a look at this df dx, you could look at this as almost, or I should write it as, at least formally, as this df. So what you're doing is adding up a lot of the changes in df in the bulk to get a net change of f at the boundary. Okay, so you could either add up all of the little changes of f in the bulk and get a net change at the boundary, or get a net change at the boundary. Okay, so that's one way to look at it. Well, how do we abstract that to higher dimensions? Okay, in particular, when we start looking at things like double integrals. All right, so if you take a vector field and you're looking at it in the region R, here in red the region is R, and it's bounded by a curve C. Okay, so one way to write that, R, the boundary of R is C. That's what we mean here. Okay, and it's going in the counterclockwise direction, C. Well, what little pieces do we have to add up in here to just end up getting a net effect at the boundary? Well, the line integrals, we talked about them being representing the circulation, okay, around. We called it the circulation. A line integral over a closed simple curve was the circulation, okay? So we could do that at the boundary. What little pieces would constitute it if we added them in the actual region? Well, what about, looking at little tiny curves around here, okay? And here I draw, like in green, I just decided to choose one of them. And I have all of these arrows going counterclockwise. And I also drew the blue over there. And again, all of these are going counterclockwise. You see, you get a sort of the blue going to the right here and the green going to the left on this line here. And now this little square does this with all of these, all right? So somehow we could add up all of the little circulations in the interior and get a net circulation at the boundary. Well, those little circulations are the curls, okay? Or you shouldn't say little circulations, but sort of an idea of what's going on, a little twistiness. You could look at the curl in the bulk, the region, or you could trade that for an operation at the boundary, the circulation, okay? So here goes yet another statement that could be summarized as trading a derivative in the bulk, R, for an operation at the boundary. Now the bulk here is R, is a region in R2, okay? And the boundary is a one-dimensional line. So the region is two-dimensional, the line is one-dimensional. Though it lives in 2D, it's line is one-dimensional. Okay? And this is the statement there. We are going counterclockwise around C, and you get this result. Okay? And you'll recall that the 2D curl for the vector field that you see there was equal to partial x g minus partial yf. Okay? That's what the curl is. So you could add up all the little twistiness inside your little region, okay? And if you add them all up in that region, you will just get the circulation at the boundary, and you could trade one for the other, okay? And notice here that if the 2D curl is 0, well, what is that? If the 2D curl is 0, then you have a conservative vector field, okay? And what's true of a conservative vector field around a closed curve? It's 0, okay? Because you start and end at the same point. So we have consistency there with the fundamental theorem of vector line integrals. Okay. We could take a look at a simple example. Consider the rotation vector field F on the unit disk. Okay. Direct computation of this, which we have done actually, we looked at the circulation of this rotation vector field around this little curve C. So direct computation would show that that line integral is equal to 2 pi, where C is equal to partial r. R is the unit disk. We're going to use Green's theorem to get the same result. So here's what we want to compute. Green's theorem tells us that it's equal to this. So we're going to compute the 2D curl of our rotation vector field. How do we do that? Well, partial g, partial x, and g here is x, okay, minus partial y of f, okay, and here is f. And so we get 2, and now this is the double integral with just a 1 in there of r, and so that's equal to the area of r, right? And the area of r, well, it's a circle with a radius of 1, so pi 1 squared, and you get 2 pi. And notice that direct computation and Green's theorem show the same result.